For this section, we are going to talk about morphodynamic modeling with Delft3D. We are going to have again two cases. Case 3 with just one sediment fraction, only sand, and case 4 with two sediment fractions, sand and mud. But before that, I'm going to show something about the previous section about hydrodynamic modeling. First, this is a comparison of water levels in Union Island and Little Berwick Station. And you see that, especially the red one, when we are in April and May, meaning that the river discharge is high, diurnal changes are much smaller compared to other times. That's the effect of the river. And our model was also showing that. So, yeah, this is what I was talking about in the first section, the effect of the river on water level during the high river season. Water level variations in the red one, which is an upstream close to the river, is much smaller. These variations are much smaller compared to these variations. And then the next thing I want to show is this is the animation of case 1, water level variation in case 1. If you look at the black areas, some areas are getting wet and some areas are getting dry in different tidal cycles. So wetting and drying is enabled in our model. Delft3D can do that. That's very important, especially for coastal Louisiana. We have low-lying lands. They are like intertidal regions. They get wet and dry in one tidal cycle. So it's very important to have these wetting and drying cycles in the model. And I'm going to show you where we apply that in the model. So let's just open, you don't need to open that. I just opened case 1 for you, just to show you where wetting and drying is applied to the model. If you go to your model setup and go to numerical parameters, you see there is a threshold here, threshold depth. We set up the threshold depth to 0.1. It means that when the water level is less than 0.1, less than 10 centimeter, it will be considered dry. If it's higher than that, it will be considered wet. So that's very important in modeling. And I forgot to say that. I just wanted to mention that. All right, so let's move on to morphodynamic modeling. Again, a review of what's a morphodynamic model. We start the model with initial bathymetry. Hydrodynamic is calculated. And then we will have a sediment transport model with different sediment fractions. For case 1, just sand. For case 2, sand and mud together. Then obviously we will have deposition, erosion, so bed level will change. Delft3D passes that updated bathymetry to the next time step. So hydrodynamic of the next time step is based on the updated bathymetry. And we do that cycle over and over again, and we can even predict the future. That's what we are going to do actually. So this is a sediment, this is an animation of sediment concentration. We just saw that. And then later, this is a morphodynamic model. We'll see how bathymetry is moving. Banks Lake Delta is growing, is bifurcating. So these are the kind of output we can get from a morphodynamic model. Now, the morphodynamic model, this is the basic equation. We have porosity, we have change in bed level. This is a transport in X direction, transport in Y direction. And also we can have subsidence, which is very important. We also have subsidence calculated, right? We have subsidence data under the Delta-X project. You can go and download that. And also we have human effects. If we have, which is important in coastal Louisiana, right? In CPRA, people, do nourishment for, conservation objectives. People, for example, in U.S. Army Corps of Engineers, they do dredging. They have dredged Wax Lake, for example. So you can also consider those in your model. So for case 3 and case 4, we are going to use RGFGRID to first make our grid. So we are not going to use Delft3D dashboard anymore. We are going to use RGFGRID to set up our grid. Then we are going to QUICKIN. These are all Delft3D tools. Then we are going to use QUICKIN to make our bathymetry. And then we are going to set up our model and run the model. Okay, so let's start with RGFGRID. I go to my Windows. Oh, sorry, my Windows, yes, it's here. And then maybe I can make a folder called case 3 in desktop. Select my working directory in case 3. Now, oops, sorry. I have to do that again. I accidentally exited Delft3D. Select working directory as case 3. Select folder. And then we go to the grid, where this is where we can make the grid. And you see RGFGRID. That's the tool we are going to use to make our grid. So we have 2 ways to make the grid, Delta3D dashboard, and also RGFGRID. This is a more power tool, obviously. You can import large DEM, large XYZ file into your into RGFGRID. The first thing I do here is to import attribute files, import open samples. Again, attribute files, open samples. And then you are going to open the DEM. The Delta-X DEM, the reduced version, the 50-meter version. Again, if you go to the instruction file, this line says reduced version of the Delta-X DEM here. In Delft3D dashboard, I imported that myself for you, the version you already had the reduced version of Delta-X DEM. But if you have not, just click here and download the DEM. Let's go back to the Windows. This is the reduced version of the DEM. Again, yeah, sure. We go to the file, then attribute files, and then open samples. Open samples, yeah. So samples are XYZ file. So this is a 50-meter version of Delta-X DEM just in the Atchafalaya region. We don't see that's very good. Let's make the legend, let's adjust the color bars. So again, I go to setting when the XYZ file is important. Go to setting and go to legend. First, here just put 0. We don't want RGFGRID to automatically adjust the color bar. We want to manually adjust the minimum and maximum depths, so we better see the DEM. Just click 0 here, and for maximum value, put 3, and for minimum value, put -3. So that's the minimum depths and maximum depths. And then click OK. So now we see better the DM, that's the delta X DM. We are going to use that to make our grid. So everybody's here. We imported our sample files, our DEM file, attribute files, open samples, and then import your XYZ file that you have downloaded from the instruction file. And then go to the setting, and then legend. Click 0 here. We don't want, because if it's 1, it means that their RGFGRID will change the color bar whenever we zoom in or zoom out. We want this to be fixed, the color bar to be fixed. So 0 here, and then -3 to 3 as the depths, and click OK. So now you should see better the DM. Now let's make the grid. So for making the grid, we go to operations. And here we see create rectangular grid. Operations, create rectangular grid. So we have a couple of numbers here that we have to put and then make the grid. The first thing we need to work on is the origin X and origin Y. That's the lower left corner of our grid. So I want my lower left corner of the grid to be here. I want to have a grid outline from here to here, the same as case 1 as case 2, but this time we are making it here. So we need to put the coordinates of lower left corner of our grid in that location. So again, open, create rectangular grid, origin X and origin Y. So what I do is that I hover over this area, and you can see X and Y information here. I hover over here. I say that this is good for the lower left of the grid. I just take a picture. That's my UTM coordinates for the lower left corner. And then I just put that and write that those numbers there. Origin X is 629668. It doesn't need to be accurate. You just want somewhere in that location. And then for the Y, it's 3243015. 6296, 6296, 68, 3243, 3243, 015. Okay. Now that's the coordinate of the lower left corner of our grid outline. And let's put it 1000. The delta X and delta Y. Let's make a large grid now, 1 kilometer by 1 kilometer. And then that's it. Just click on OK. That's our grid. That's 1 kilometer by 1 kilometer grid. So now it's time for a little bit, adjustment. The first thing I do is that I want the left corner to be a little to the left, because here it's touching the apex of this island. I don't want my open boundary. I will have a lateral boundary on the west. I don't want it to be on the land. I don't want it to touch any land. let's move it a little to the west. And we do that by adjusting the coordinate of the lower left corner. So I hover over again here, 62. I just need to adjust the X coordinate, right? Let's take another picture. Thing here is good. Maybe a little to the left. Operations. Again, you can go to operations, create rectangular grid. Actually, first let's delete the grid that you just made. So operations, delete, and then delete grid. So again, operation, create rectangular grid. And I want to adjust the X coordinate so it can be a little to the left. 6280, 8082. Okay. Now it's better. I'm not touching this area. I want it to be a little to the left of this land here. Okay, so now I want to check my northern parts where I have river. Okay. Now, if you look at the northern boundary, we are a little bit on these red areas are river. They have higher depths. I want it to be, on this narrow portion of the river, so it's easier for me to make my river boundary. So how do I do that? I go to operations, create rectangular grid, and these are, the first line says the number of grid in M direction. M direction is the horizontal direction. And the second one is number of grid cells in N direction. Both are 50. We are going 50, 1 kilometer by 1 kilometer to the right, and we are going 50, 1 kilometer by 1 kilometer to the north from our lower left corner. So let's just, maybe for the N direction, which is the vertical direction, let's just put 48 instead of 50. So we bring down a little bit our grid, maybe 48. And then make the grid again. Let's zoom to see if it's okay or not. So it's on this narrow section. This one is here. I want it to be actually here. So 1, 2, 3, I want to reduce 3 more. So go to operation again, create rectangular grid. And here just put 45. Now let's zoom. Now our grid is this narrow portion of the river. This one is also on this narrow portion of the river. It should be okay for us for later to assign the river boundaries there. It's always, I suggest you to put your river boundaries in a narrow section of the river. Adjust your grid in a way that the end of your grid is located on the narrow section of the river. So later we can easily define the river boundaries. You'll see how we define the river boundary later. Now I'm okay with this grid. Let's take a look. On the south, we will have one south boundary here. On the west, we will have one lateral boundary here. And then we will have 2 river boundaries, one for Wax Lake River and one for Atchafalaya River here. But 1,000 meter or 1 kilometer is very coarse. We want to refine the grid. How we do that? First, we go to the setting, and then we go to the general. So there is a refinement factor there, N refinement factor and N refinement factor. So we want the refinement factor to be 10 because we have a resolution of 1,000 meter, and then we want to refine it to 100 meter. So we have a factor of 10 between a 1,000 meter grid and a 100 meter grid. Just we need to put 10 there. Okay, so 10, that's in the setting now. And then I go to operations, and there is an operation there called regular grid coarseness, and then click on refine. Now the grid converted to 100 meter. We had a 1,000 meter grid, now it's refined to 100 meter. If you want to make sure, just zoom to your grid, and you see the grid here. That's 100 meter grid. Pardon me?
So you went from 1,000 and you did an refinement to that 100. But would that have been the same thing if you just started with 100, or is there a difference?
It's just I suggest you to start with a coarse resolution like 1,000 meter, because you want to adjust your grid, and you say that okay, I just need one row below for those rivers. If it's 100 meter, then I have to calculate how many rows should I come down. It's just easier to start with a coarse resolution, and then you refine it. So that's our grid. There are many options actually in RGFGRID. It doesn't look that complicated, but it has many options. We are using the very simple way of making grid. Yeah. So when you are done with the grid, you just go to File and export your grid. Don't forget to export your grid. You have a question? Okay. So we export your grid. Sorry, 50 to 45. It doesn't look correct. Maybe it's the original one. Okay, so export grid and change the name to, actually go to the desktop and go to case 3 because we are running case 3 and that's our grid file. And just change it to case 3. Case3.grd. That's our grid file. We are done with the grid now. Now we need to make the bathymetry file. So close RGFGRID. I don't want to, if you want, you can save it as a project. I don't want to do that. Just click yes. So now go to QUICKIN, the second option. QUICKIN. Okay. Again, the first thing we do is to open samples. We are going to open our DEM files. And then find your reduced version DEM file, the XYZ file. Open that in QUICKIN. You see the operation on the right down. It's opening the file. Here it's open. Again, we don't see that well, like what we did in RGFGRID. Go to the setting, go to the legend, click 0 here to avoid auto scale legend, and click -3 to 3, and then click OK. something was wrong. Zero number of digits. Oh, sorry. So minimum value should be -3. Maximum value is 3. Why is it not changing? Okay. So we see the grid. We see the DEM now. Now we have to import the grid we just made. Import the grid. So file, import grid. File, import grid. You open your grid. So it should be in your folder case 3. Open the grid file here. That's our 100-meter grid file. Let's zoom to the grid to see what's happening there. Zoom more, zoom to the grid scale. So you see what's going on here. We have 100-meter grid, and our DEM was reduced to 50 meters. So obviously we have 4 points in each grid cell. So we have 4 points of DEM in each grid cell. Now we want to assign one value to each grid point. And how we do that, this is how we make the bathymetry file. We go to operation and then click on grid cell averaging. It's basically averaging those 4 points and assigning that to each grid point. So grid cell averaging. That's it. We just made our grid file. Let's zoom back. And let's turn off everything else so we can just see our bathymetry file. So go to settings and, oh no, sorry, go to view and go to grid. Select no grid. We don't want to see the grid now. And then go to view and then go to samples, no samples. So samples is the name of the DEM. The Delft3D for some reason chose samples for DEM XYZ files. So no samples. That's our bathymetry file. So it's time for us to export the bathymetry file. Go to File and Export Depths. And save that in case 3 folder. Case 3. Save it. All right, now we have the depths file, the bathymetry file, and the grid file. Let's set up the model. For setting up the model, go to Flow and Flow Input. Okay, and then start from the description. I just write delta X workshop case 3. That's our case 3. And then go to the domain. So everyone is here. We went to the flow inputs. We just wrote a description here, whatever you want. And go to the domain. Now we are going to open the grid file here. That's our grid file. Now our enclosure file. So now we just imported our grid file. It's time for the bathymetry file that we just made. Go to the bathymetry tab, file, open. Case3.dep is our bathymetry file. Open that to the model. I forgot my glasses. We just imported the grid file and the bathymetry file. And now it's time for time frame. So again, we are going to run the model from January 1st, 2024. So change the time frame to January 1st, 2024 to We are going to run the model for 10 days. So this time from January 1st, 2024 to January 10, 2024. And let's just put the reference time as the starting time. That's just an arbitrary reference for the time in Delft3D. And we are going to use a time step of 1. We reduced the time step. Who knows why? Why did we reduce the time step from 4 minutes to 1 minute? Because we are still using 100-meter grid. Sorry? But I mean, in case 1 and case 2, we also have 100-meter grid resolution. Here also we are using 100-meter grid resolution. But it's better to reduce the time step. If we don't do that, probably the model will blow up. Because of the Courant number is different for shallow water equations and advection equations. In this model, we are going to add the sediment model and sediment fractions. So in addition to the shallow water equations, advection and diffusion equation will be solved for sediment fractions. And the Courant number is more sensitive for advection diffusion equation. It's better to keep the Courant number below 1 for a model which has like sediment or salinity, where advection diffusion equation will be solved. But for hydrodynamic model with just shallow water equations, you can maybe have a Courant number up to maybe, I don't know, even 5, 6. You have to check it, of course. If your Courant number is above 1, you have always, you have to check the results. Actually, you can check the Courant number in QUICKIN. I wish, let me actually show you where you can check the Courant number, because that's a very useful tool. Confused between these two. In GRID, in QUICKIN. When you made your bathymetry in QUICKIN, you don't need to follow me on this. I just want to show you, and it's recorded. You can watch it later. Let's say that we just made our bathymetry here in QUICKIN. If you go to the setting and go to the general, there is a time. This is time step for Courant numbers. And it's in seconds, right? And we are going to use 1 meter, which is 60 seconds. So let's keep it at 60, click OK, and then go to operations. And here we have Courant numbers. You see Courant numbers? What we are seeing now is not the depth, it's the Courant number. Let's actually turn off the grid. I don't want to see the grid. This is our Courant numbers. So most of the areas are blue with 1 minute. And this is showing our Courant number. You can check Courant number. It's better, especially on your boundaries. It's better not to have high Courant numbers. Keep it below 1 if you have salinity or sediment in your model, because advection diffusion equation are going to be solved. And if it's just a flow model, you probably can have a little bit higher Courant numbers. So that's a very useful tool. Obviously, it depends on your model settings too. In river settings, in which we have like a unidirectional flow, you can have higher Courant numbers. It's not a big deal. But on open boundary, it's better not to have it. For our case, we are a little sacrificing, Courant number criteria, and it works for us. So this is how you can check Courant numbers. We are setting up our model. We passed the description. In the domain, we imported the grid file, the enclosure file. So always the grid file is coming with two files. One is called the .grd, one is called .enc. Those together work as one grid file. And then we imported the bathymetry. And then in time frame, we set up the model from January 1st, 2024 to January 10, 2024. Yes, Tom? Yes, thank you. So January 10, 2024, and then the time step is going to be 1 minute. And then let's go to processes. This is where we add the sediment model. So you see here sediments, click on it, and then here modify the sediment name to sediment __ sand, because in this case, in case 3, we are going to only have sand in the model. And then the type of the sediment is non-cohesive, because this is sand. So then click add. We just added one sediment fraction to the model, which is sand, and it's non-cohesive. And then you can close it. Then click OK. If something pops up, it's OK. Click OK. So we just added one sediment fraction to the model. Everyone could follow me on this? OK. Now let's go to initial conditions. For initial condition, 0 water level and also 0 sediment concentration. And then let's go to the boundaries. OK, here is where we add boundaries. So you can go to view and then visualize area. It's better to maximize the window. And then click view and uncheck grid. So we see what's going on. And then click on colors and change the colors to bathymetry rainbow. Okay, that's how we visualize our model setup. Let's add the southern boundary first. So you go to the edit. The edit is on open boundaries. It means that we are editing the open boundaries. And then click on edit and add. The edit mode should be on add. So edit should be on open boundaries and edit mode should be on add, because we want to add an open boundary. And then for the, like what we did in Delft3D dashboard, click and drag and make your open boundary here. That's our south boundary. Actually, whenever I make a boundary, I just minimize this and then click on the name. I immediately rename it to south boundary. And then again, let's add another boundary for the lateral boundary. So it's for some reasons for the west boundary, I sometimes have to do it a couple of times. So you may have the same problem here. Okay. I just did that. I call this boundary as west boundary. Now it's time for river boundaries. So let's go back to the visualization area. Now you get why we adjusted our boundary, our grid, so it falls into a narrow portion of our grid. So again, edit is on open boundary, edit mode is on add, and then just click from here to here. This is my Waxley river boundary. Now we just have one more boundary to add. Here. Again, just click from here to here. It's not that important to be very accurate. And then I click this one. I rename this one as Achafalaya because this is my Achafalaya river. Yes. If you couldn't, I'm going to give you an alternative to do it now so we can proceed, because it's hard for you to drag and make that open boundary. We are going to work on the case 3 folder that you downloaded. It's ready, everything is ready. We are going to just review everything, yes. Yeah, that's right. So it's a very good point. Actually, instead of dragging your open boundary, you can give the coordinates of your boundaries. But for now, let's change the working directory to case 3. The case 3 folder that you downloaded, not the one that we were working right now. And I'm going to show you everything there. So this is the case 3 that you have downloaded, probably, case 3 folder. Change the directory there, and then go to the flow inputs, and file, open your case 3, open the MDF file. So this setup is complete. And let me show you what's going on here. First, go to the view, visualize area, uncheck grid. So you see in this model, this is case 3, we have a source boundary because we had problem dragging and making this boundary. We just skipped this. We went to the downloaded ready file. It has everything. We have source boundary, we have a lateral boundary at the best. And also we have 2 river boundaries on top, Baxter River, and also 2 monitoring stations, M1 and M2. Those 2 are monitoring stations. So this is our setup for case 3. And let's review the process. This is checked. This is for sediment. And then if you click edit, there is sand included in this model. It's a non-cohesive model. And then go to physical parameters. Actually, let's go to boundaries. For the south boundary, if you click on edit flow condition, we are only using 2 components, K1 and O1. For the west boundary, we are using a Newman open boundary. Newman open boundary is a kind of boundary which is the best choice for lateral boundaries, because especially when you have a small model, you will have, non-uniform along-shore water level gradients. Water level is solved inside your model based on shallow water equations. And then you have a lateral boundary, and you want to assign a water level to this lateral boundary. If this is different from the water level which is calculated in the model, if this is different, there will be some turbulences in the model, and your model will crash. That's why we choose Newman open boundary. And with Newman open boundary, we are telling the model that a longshore water level gradient is uniform. Basically, we are saying that in the lateral boundary, choose water levels calculated inside the model. So the flow can go in and out from the lateral boundary. For the Wax Lake River, we are importing 3,500 cubic meter per second. And again, negative numbers means inside, they are going into your model. And for Atchafalaya, which is a bigger river compared to Wax Lake River, we are assuming minus 4,500. And then this is for just boundary conditions for the flow model. We have another option here, which is for eddy transport condition. This is our boundary condition for the sediment model. Let's start from the south boundary. So we don't want any sand to be imported to our model from our south boundary. So let's just put 0 everywhere, 0, 0, 0, 0. Yeah. Yeah, sure. Okay. So anybody has questions now? So what we are doing is reviewing case 3. We went to the downloaded folder, case 3. We opened the MDF file. We visualize the area. We had one south, yes? Okay, let me show you. Yes, so select your working directory as case 3 folder, the one that you have downloaded, okay? And then this is the Delft3D main menu, and then go to flow, and then flow input, and then file, open your case3.mdf file. Okay, all right. So everything is there. The main difference between this one and the previous cases is the process part. If you go to the process, we have checked sediments. It means that we are going to add sediments to this model. And then click edit. You see that we have added sand, which is a non-cohesive sediment. We have also option for cohesive sediments, which we will add in case 4. And then initial condition, boundaries. We are talking about boundaries now. So we talked about flow boundaries. Now we are going to talk about sediment boundaries. We don't want any sand to be imported to the model from the south boundary. And for the west boundary, everything should be 0. No water level gradient in the lateral boundary. Oh, sorry, we are talking about sediment boundary, sorry. So we don't want any sand to be imported to the model from the west boundary. All our sediments are coming from the river. So no sand coming from the west, no sand coming from the south boundary. So let's go to the Wax River. This is our Wax River boundary. And and we have put 0.2 kilogram per cubic meter as our sand concentration. It means that it's the concentration of sediment that come into our domain from the Wax Lake River. And the same thing for Atchafalaya. So the concentration of sand coming to the domain is the same in Wax and Atchafalaya River, 0.2 kilogram per cubic meter. That's our boundaries. Then we go to the physical parameters. We don't touch anything here in constant. In roughness, we are using a uniform value, Chesy 65. And let's go to the sediment. This is an important part. So for sediment section, sediment tab here, we don't touch anything. But this one by default is, I guess, 200. We change it to 140. So it all depends on the dimension of the D50 of the median diameter of your sediment sizes. It's either based on field data usually that we get this information that how much is the, what's the size of sand, what's the size of mud in our model domain. So we choose 140 here. Yes. Usually we define the sediment fraction based on D50. Yeah. And then the uniform, that's the initial sediment layer thickness. We put that as 5 meter here. And then go to the morphology. That's an important part. We have a morphological factor of 365. What does it mean? It means that we are running the model for one time step and calculate the erosion and deposition rates. And model will multiply that by 365. We are running the model for 10 days. So 10 days times 365, we will have 10 years of simulation. That's how we simulate a morphology, how we set up a morphology model. Morphological processes are very slow, right? We cannot run the model for 100 years and then it's not practical, right? So that's a solution for this. We can assume that changes in one time step can be expanded to longer time steps, longer time scales. So every time step is the rates of deposition and erosion are multiplied by 365. So if you remember, we are running the model for 10 days and we are including 365 as morphological factor. So we are running the model for 10 years. And that's it. We have monitoring stations here, outputs. Then it's time to run the model. So let's close it and then go to start. Select the MDF file, case 3 MDF file. Okay. So the model starts and it will take 3 hours, about 4 hours to run 10 days of morphological model. Who knows why this is much higher than the 15 minutes that we have for case 1 and 2? Why is it taking so much longer? Smaller time step, yes, we were using 4 minutes for case 1 and case 2, but here we are using it 1 minute exactly, but there are no reasons for that.
Okay, you transport equation.
Exactly, yeah. The main reason is that in case 1 and case 2, we were just solving shallow water equations. Here we are adding advection diffusion equations and so many other equations to the model. That's why it's taking longer. So just run it for a few minutes, maybe stop it. We're going to visualize the results. For visualization, we go to QUICKPLOT. And then let's open case 3 output folder. Let's go to case 3 output folder. We didn't change our working directory, so be careful to choose case 3 output folder and then choose the map file. Okay. Now, then scroll down here and choose bed level in water level points. So we are going to see the bed level changes through time, 10 years of simulations. Okay, bed level in water level points. And then I like horizontal color bars. I click on that and then click, actually, let's show you something. So if you check show times here, show time, you see the times, but these are normal times, 10 days. If you go to here, this one, this option here, it's called set file dependent options. Then you have to you have the option to change the display time from hydrodynamic to morphodynamic. So change it from hydrodynamic to morphodynamic and close it. Now you see the chart, the time have changed. Now the last time step that we have output belongs to 2033, almost 10 years. That's what we want to simulate. From 2024, January 1st, we started, and we are ending on 13 December 2033. That's happening because of that morphological factor, 265. So now here on color limit, again, I want to prevent it from automatic, scales. Let's change it to manual and change it from -3 to 3. Again, for color limits, from automatic to manual, and maximum 3, minimum 3. Oh, yes, thank you. -3 to 3. And then we can now click on quick view. Let's zoom a little bit. And let's make it a little bigger. Okay, that's how our bathymetry looks like after 10 years. Obviously, we have a coarse resolution model. Our setup is not accurate. When we see that bathymetry has changed, we see that the delta, especially backslash delta, has developed. It's different from its initial condition. So noticing the differences between the bathymetry from the current condition, January 1st, 2024, and then next 10 years, it may be a little hard because this model is only having sand, and with sand, we will not have that much change in bathymetry. That's why we are going to have case 4 with sand and mud together. Most of the sediment here is mud. That's why we need to add mud, and then we will see more changes in bathymetry. If you want to see the changes in bathymetry, you can obviously make an animation here using this option. You can make an animation, save it to a video file, and then you can see over time how your bathymetry is changing. Just the same as making an animation for water level, no difference. We need that, right? Now it's let's see what happens if we add mod. I'm going to jump into the results immediately, but then we are going back to case 4 and see the setup of case 4. But here is how they are different in case 4, case 3, sand only, and case 4, sand and mud together. So in case 3, these two animations are showing sediment concentration. This is just sediment. So you see that in case 3 that we have sand sediment concentration is lower because sand is heavier. It's not going to move that much. It's mostly local resuspension and deposition. But mud is lighter, is transporting from the river in the offshore area. You see that it's moving much more compared to sand. And also, if you notice in this model, you can see that the delta are changing. It's changing a lot. Actually, backslash delta is developing along that direct channel that happens when you have a direct channel. you are going to deposit on the side of the channel and also erode the main channel. So you see that the delta is developing. That's the difference between case 3 and case 2. Case 4 and case 3, sand only and sand and mud. And now this is a difference in morphology. When you only have sand and when you have sand and mud together. You can compare them together, and obviously the change in this case is much more realistic. As these deltas are developing more naturally, and that's because just we have included mud in the model. So we saw the setup of model 3. Now let's see the setup of model 4, sand and mud together. Okay. So again, open Delft3D, change your working directory to case 4 output. No, sorry, case 4, the one that you have downloaded. We are not going to make everything from scratch again. Just you want to open the setup and see what's happening inside. So select your working directory to case 4. You have downloaded this folder. And then flow inputs, file open, in case 4.mdf file, the metadata file. So there's a description here, sand and mud. There's no difference between these two cases, except in this section, go to the process. And if you click on edit, you see that we have two sediment fractions here. One is sand, which is a non-cohesive sediment, and the other one is mud, which is a cohesive sediment. So we have added two sediment fractions in case 2, right? And then obviously, if you go to the sediment section in physical parameters in sediment sections, because we have added another fraction, we have two sections here. One is for sand. We are using the median diameter of 140, initial thickness of 5 meters. For mud, it's very important, this value here, the settling velocity, 0.3. That's what I'm using for my main models, actually, not just for the workshop. And why I have reached to this number, 0.3, that's a matter of calibration. And how you can calibrate your model, you can use TSS data from AVRIS-NG. You can use TSS data from AVRIS-NG. These are sediment concentrations. We have so many acquisitions. You can run the model with different settling values. That's 0.3 that I told you. You can run it by 0.1, 0.2, 0.3, even smaller numbers. And then compare your results with these sediment concentrations and try to reduce your error. So usually we have, if we are lucky, we have like some measurements in limited points for sediment concentrations. But now we have like a map of sediment concentration using AVRIS-NG. This is a great data. You can download, if you want to know more about AVRIS-NG, you can refer to the previous workshop recording. That's my colleague, Daniel Jensen. Here he talks about AVRIS-NG product, and yeah, you can learn about this. And if you want to download it, there is a link in the instruction file here. This is the landing page for AVRIS-NG. Water quality and TSS data. You can download this data. And obviously, again, as I suggested to you, start working with QGIS, you can import your files in QGIS and process them, or use the Mosaic. Are the Mosaic files in the RNL website, or just TSS especially? Yes. Okay. Actually, if the Mosaic file is the file that all the individual what do we call them, acquisitions, individual acquisitions are merged together, like this one. I don't have it here actually.
Yeah, you have to be careful with the dates.
Exactly. Even if you have the Mosaic file of the TSS, it's better to work on individual acquisitions because you want to compare your model with the exact time and date of the model. For example, this one, these two are two different acquisitions. The time of the acquisitions is here. One is 20 August 2021 at time 2:21 in the afternoon. This one is for some time else, another time. So it's better to compare your model with acquisitions. For example, this is a process I have done to calibrate my model. Here we see model minus AVRIS-NG in this acquisition. As you see, at the beginning, I've had large errors. These red areas means I've had so much difference between the model and AVRIS-NG TSS data. But after a couple of calibration, I have significantly reduced the error. Now, most of areas are yellow, which means close to zero. That's how you can use AVRIS-NG data, TSS data to calibrate your model. Who had the question? Yes. Your question is about the... yes, actually, you can download the whole data here. And then you can see in the names, it's 2021. It's March, January, March 27, and this is the time, right? Am I right? This is the timing. It's easy. Actually, it's a NetCDF file. You can open it everywhere and work with it. With this, how much time do we have? 10 minutes. That's it. We ran two cases. Case 3 with only sand, and case 4 with sand and mud. And we saw that the difference is a lot when you have more sediment fractions. And we saw how we can use, for example, AVRIS-NG TSS data. In the first section, we learned how we can use vegetation maps to modify our bottom friction, the model bottom friction, and improve the results. And we have 10 more minutes. If you have any questions, let me know. So that's where our initial stratigraphy plays a role. The question is that we have a bathymetry in the model, right? But where do we define that what's included in that bathymetry? What's the material of that bathymetry? So let me actually go to the setup. So initial sediment layer thickness at bed, that's where we are telling the model that assume that we have 5 meter, that's the thickness of sand. That's because this is sand. Also, we can define the same thing for mud. Or we can import a file, if we want to be very accurate. Import a file and tell the model that we have especially varying materials. In this location, we have this fraction of sand. In this location, we have this fraction of sand. We can do that in Delft3. But for these simple cases, we are assuming 5 meters of sand and 5 meters of mud.
So when you do that, they're both within the same 5 meters. So it's 5 meters of sand, 5 meters of mud. It understands it's 5 meters of both of them within the same 5 meters. Or it's 5 meters on top of each other.
No, it's not 5 meters on top of each other. It's you're actually telling the model that the sediment fraction is 50%, 50% sand, 50% mud. Actually, you can see that change in sediment fraction. Let me show you. It's good because we have time. We can see how sediment fraction changes. I'm going to open the output of case 4, where we have both sand and mud, and see how sediment fraction changes. This one. And then before that, let me show this. This is very important. So you have this option to see the cumulative erosion and sedimentation. Let's click on that and then change the manual. Let's say -1 to 1. Central, click view. So this is the bathymetry in the last time step minus bathymetry in the first time step. So we can see that mostly at the middle of the channels is blue, which is negative. Based on the scale bar, it means that we have erosion at the middle of the channels. And then at the end of the channels, we have deposition. That's how bifurcation occurs. Sediment is transported from the river into the channels and will be deposited at the end of the channel. And then it erodes the middle, goes, then it bifurcates. So usually we have deposition at the end of the channels. So that's what you can also analyze and see in the output of case 4 and case 3. And if you compare it, case 4 with case 3, you see that deposition and erosion is less in case 3 compared to case 4, because case 4 is including mud and sand. Okay, back to fraction. Okay.
Yeah.
In 10 years, erosion of 1 meter, deposition was 1 meter or erosion? It can be in some places in 10 years. I guess it can be, but obviously these models are not, calibrated, or we should validate this. But I guess in 10 meter, maybe, I'm not sure. So, oops. Again, sediment fraction. I hope I can find it. Sediment volume fraction here. So this is sediment volume fraction mark. And then it basically means if it's 0, it means that we have more mud in that location. If it's blue, we have more mud. And if it's 1, we have more sand. That's not the input. That's the input was, if it was the input, everywhere should be green. 0.5 means 50%, 50%. After 10 years, it has changed. And we expect that because at the middle of channel, we expect to have more sand. Right? It's heavier deposits at the end of at the middle of the channel. But at the end, on the sides, we will have more mud after if you let the model go for a while.